Hi everyone, we're live from the cage, and welcome back to another splendid installment of Good Morning, the 119th Element. With me today, as always, is my partner in science, James Tully. Joining us are two expert elementologists, the top in their field, Drew Ross, who is a doctor, and Cole. Welcome, fellas.
It's good to be here.
Indeed, it is.
So, Drew and Cole, we heard that last week you had discovered a new element. There were only 118 elements known, but with your findings, there are now 119. What are the properties of your new element? Where is it found? What is it? How abundant is it?
Whoa. Hold your horses there, Matt. Before we get into that, let's take a step back for a second and look at the basics of elements.
Sure thing, James. So, Cole, where do elements come from?
That is quite the question there, Matt. Simply put, elements come from stars.
That is correct. In the cores of stars, nuclear fusion occurs, which combines smaller atoms into larger atoms. For example, hydrogen atoms, each of which have one proton, are fused into helium atoms, which each have two protons.
Does this process only occur up to helium?
No, nuclear fusion in the cores of stars is capable of creating elements up to iron. Elements with more protons than this are created in the explosions of stars known as supernovae.
When does this happen?
Well, near the end of a star's life, it inflates into a massive star known as a red giant before exploding. All the elements in the star, as well as those with more protons than iron formed in the explosion, are then dispersed throughout the universe in massive pools known as interstellar clouds.
Well, if elements come from stars, then where do the stars come from?
So, you want to know how the universe began?
Well, I guess you could say that.
Well, the dominant theory right now is called the Big Bang Theory, which states that all mass in the universe was at one point compressed into one tiny little point before rapidly exploding outwards in all directions.
So, if all stars are made of basically burning elements and all elements come from stars, what makes each element different from another?
Elements differ due to the number of protons present in them. Protons will determine the element that is present. For example, magnesium has 12 protons and silicon has 14. The elemental difference between the two atoms are all because of the difference in protons.
Oh, that makes more sense. But I'm not to stop you there, so we can hear a quick word from our sponsors. This podcast is brought to you by the up-and-coming Spaghetti and a Haircut Barbershop on Route 40. Enjoy a nice bowl of spaghetti while you get your hair clipped by our finest professional hair cutters that have been through 20 years of haircutting school.
Welcome back, folks. Before the break, Drew and Cole were telling us about how atoms of different elements vary. But I'd like to know how atoms of the same element differ.
Well, James, atoms of the same element all have the same number of protons. However, they can differ in the other two parts of the atom, neutrons and electrons. I'll start with the neutrons. So neutrons, in addition to protons, both of which are in the atom's nucleus, contribute to the atom's mass. For every one proton or neutron, the atom gains one atomic mass unit, or AMU for short. Different atoms of the same element can vary in their number of neutrons and therefore can have different masses. An atom that has a specified mass is called an isotope. For example, silicon-32 is a silicon isotope that has the normal 14 silicon protons as well as 18 neutrons, giving it a total mass number of 32 AMUs.
The other way atoms of the same element can differ has to do with electrons. All electrons have a negative charge, whereas all protons have a positive charge, and neutrons, which have a neutral charge. So they're not really important in this regard. Because of this, when an atom has the same number of protons as electrons, their charges cancel out, and the atom is said to have a neutral charge. However, when the number of electrons and protons is not equal, the atom is called an ion. More negative electrons and positive protons makes the atom a negative ion, also known as an anion, whereas the opposite case with more protons and electrons makes the atom a positive ion, or a cation.
That all makes sense. But I've heard a lot of people hooting and hollering about something having to do with unstable atoms and deadly radiation that results from them. Does this have anything to do with these differences in atoms?
Sort of. To really understand radioactive decay, you have to first understand how an atom is held together. You see, due to the electromagnetic force in the universe, all positive and negative charges are attracted to each other, but things with the same charge repel to each other. This becomes a problem when there's all these protons with the same positive charge packed into the nucleus of an atom. The electromagnetic force makes them repel repel each other. However, there is another force present in our universe, the strong nuclear force, which is much stronger than the electromagnetic force, so it is able to cram all the protons in an atom. However, the strong nuclear force is only effective over small distances, so as the amount of protons and neutrons in an atom increase, the electromagnetic force become a larger and larger influencer. This is why more massive atoms, like those of uranium, are more unstable.
And how does this relate back to radioactive decay?
Well, you see, atoms don't like to be unstable and will undergo radioactive decay when they are. There are two types of decay that occur to return the balance of neutrons and electrons, alpha and beta decay. Alpha decay occurs when the proton to neutron ratio in an atom is too high, so 2 protons and 2 neutrons are ejected. Beta decay, on the other hand, happens when an atom has too many neutrons, so a neutron turns into a proton and ejects an electron.
Well, that's great and all, but should I be worried about these emissions?
No, these types of radiation are very weak. Alpha decay particles can be stopped by just a sheet of paper, and beta decay particles by some aluminum foil.
Oh, that doesn't sound hard. Why does everybody make such a big deal about it then?
Well, you see, there's another type of radiation that'll really mess you up, gamma radiation. It happens when an atom gets real excited and shoots off a high-energy gamma wave. This type of radiation is hard to stop. You'll need a block of lead or a good amount of earth to stop it.
Ouch. Does radioactive decay have any other functionality?
Yes, it does actually. You see, a half of the quantity of a certain isotope will decay into another atom in a consistent time. This is called an isotope's half-life. So, for example, if you have 100 atoms of one element and after 3 minutes there are only 50 undecayed atoms left, the atom has a half-life of 3 minutes.
And how is this useful?
Because each radioactive isotope has a consistent half-life, scientists can measure the amount of the original isotope and the decayed isotope in a sample of something and figure out how old that thing is. This can be used to find the age of things like planets and was used to discover the age of Earth through the use of this technique on asteroid fragments on the planet that formed at around the same age the Earth did.
Wow, that's sure fascinating, but I'm going to have to stop you there again and hear a word from our final sponsor. Wow, Drew, you smell good. You must be wearing Old Spice fragrances. Old Spice is a popular men's grooming product designed to make you smell your best. Use code SPECTRA to get 20% off your next order. Old Spice, when, why, how, because.
Welcome back from the break. We left off with how humans use radioactive decay to find the age of planets.
Yes, that was very interesting. But what I'd like to know is if your 119th element is radioactive.
As a matter of fact, our element is radioactive. Our element has 119 protons. However, there are many isotopes to it. There are many properties of our element and every other element.
So every element has 3 main properties: atomic radius, ionization energy, and electronegativity. Atomic radius is the radius of an atom. As you travel down a period on the periodic table, atomic radius decreases, and as you travel down a group, it increases. This occurs because as you travel down a period, the number of protons and electrons increases, and so does their electromagnetic pull on each other, causing them to be pulled closer together and decreasing the radius. The converse of this occurs when traveling down a group, because each new level introduces another energy level of electrons, resulting in a phenomenon called shielding. This means that the electrons closer to the nucleus take up more of the attractive positive force, so the outer electrons are less affected by it, thereby causing the electrons to be more spread out and increasing the radius of the atom. Ionization energy is the energy required to take an electron away from an atom, and it increases as you go down a period and decreases as you descend a group. This happens because of the same occurrences in atomic radius. More protons equals more pull on electrons and therefore more energy to take them away. And more energy levels equals more shielding, so therefore less energy needed to take them away. Lastly, electronegativity energy is the energy required to pull an electron towards an atom. This also increases as you go down a period and decreases as you go down a group for the same 2 reasons. More protons allows the atom to have a greater pull on free electrons, whereas more shielding lessens this effect.
Wow, that's a lot of information to take in, guys. However, that is very interesting to know about atoms. One who doesn't major in the field of science would not have any idea about those 3 topics. Now, of my knowledge, I have heard something about waves and stars. Can you explain more about this topic?
Well, firstly, all light, both visible and invisible, is made of wavelengths. The shorter the wavelength, the higher the frequency and energy, and vice versa. Every atom emits a certain wavelength of light, which can be seen on an emission spectrum. By looking at a star and the wavelengths of light it produces, you can find out what kind of atoms are in it. This allows a number of inferences to be made about the star.
Yes, that is right. These inferences include the elemental composition of a star, the star's temperature, because certain atoms exist in certain temperatures, density, because of the number of atoms present in the star, magnetic fields, because of how they can change the way emissions appear, and motion.
Whoa. Motion? How does that work?
Well, you see, Matt, this can be discovered because of something called the Doppler effect. As light-emitting things move away from the observer, the wavelengths they emit appear longer and therefore look more red, whereas when they move closer, the wavelengths appear shorter and the thing looks more blue.
So is this how you discovered this new element?
Exactly. We looked at a very far-away star system with these new powerful telescopes and noticed a unique emission, proving an exciting new discovery.
Very interesting. Well, that's going to have to be all for today, folks. I'm so glad that we had these two elementologists join us on this podcast today. We were able to learn a lot about stars, elements, and waves.
To recap, what we learned about the 119th element is that its name is New Elementium. It has an average atomic mass of 297 AMUs, and it produces the color green on the emission spectrum. It is only present in some distant stars, and there are some isotopes of New Elementium. Drew and Cole trying to break down the rest of the mechanics of stars. To be sure to check out their findings in the news sometime soon.
Thank you for tuning in to today's podcast. Signing offline, I'm Matt.
And I'm James.
Be sure to tune into our next podcast. Never.